So, eTES, there certainly has been a major increase in not just the discussion of these technologies, but also the number of solutions available in the Australian market. Happily, too, we're seeing a number of installations proceeding in other markets and in Australia as well. More and more industrial businesses are considering eTES as a way to manage energy costs and decarbonise their process heat. With Australia's rather volatile electricity market, there's a great opportunity to store thermal energy during times of low or near zero cost electricity for use later. Now, we have a fantastic panel of presenters for you today. First, we have Professor Joe Coventry from the Australian National University, who will provide an overview of the eTES opportunity in Australia. Next, we will have Kris Nelson from Knode, a renewable heat project developer. He will be discussing his company's work with MGA Thermal and an upcoming project. We will then have the end user perspective with a joint presentation from Lawry from Deta and from Mark and Lenin from Lenin Services Australia, discussing their recently completed thermal storage feasibility study. But first, Professor Joe Coventry from ANU. He's a researcher and engineer experienced in the development and commercialization of concentrating solar and energy storage. His present focus is on industrial decarbonisation, particularly the integration of thermal energy storage with industrial processes, including alumina, iron and steel, and the paper sectors.
Thanks very much, Laura. Um, so today I'm going to just give I guess, a bit of a high-level overview of thermal energy storage, looking at the technologies themselves as a kind of intro, I guess, to the other speakers. But before I do that, I'd just like to also add my also pay my respect to the Ngunnawal and Ngambri people, the elders past and present. I'm based here in Canberra. And also to any First Nations Australians joining the call today. Just a brief outline of the talk. As I say, it'll be fairly high level for mine, just looking at different kinds of thermal energy storage technologies, and then I'll run through just a few case studies to kind of set the scene, both in Australia and some international ones. As a bit of a background, I guess we all know that heat is a major contributor to global greenhouse gas emissions. The picture's fairly similar across most industrialised nations, although in Australia we have quite a large use of heat in our alumina sector, both in high temperature heat and also in the calcination, and also in sort of medium temperature heat in steam, in the digestion. And in other parts of the world, iron and steel is probably more dominant, although mostly that's due to coking coal use in blast furnaces. So we can see in these plots, both in Australia and around the world, heat's used across many different sectors and also across a really wide range of temperatures. So eTES is a great technology to really span across that wide range of applications. We know well, this audience would know very well that there's quite a range of different options for decarbonising heat supply, as listed here. But why would we potentially choose thermal energy storage? Well, I guess some of the key reasons listed here are that it can lower operating costs by charging during periods, low price periods, and then use the storage to ride through high price periods. If you happen to have on-site renewable energy or near-site renewable energy supply, say from PV or wind, then it can help buffer that intermittency that you get from the source of energy. But it's also worth mentioning that thermal storage can also be a buffer on the demand side as well. And there's one of our case studies later, an abattoir. That is certainly the case, and why thermal storage was important. I'm just going to run through basically a little bit of a technology overview in this talk, classifying thermal energy storage into three different categories: sensible heat storage, latent heat storage, and thermochemical storage. Sensible storage is effectively where the that as you put energy into the storage, the system increases linearly or near linearly in temperature. Latent heat storage involves a physical phase change, and as you put heat in, you're operating at a constant temperature with phase change materials. And thermochemical energy storage involves reversible reactions. Generally, I note that sensible storage is more mature than the other types of storage, and a lot of the startup companies that we're seeing emerging in the market are using this type of storage technology. So I'll first run through just some of the basic thermal storage, sensible thermal storage technologies. Perhaps the simplest and most widely deployed is hot water storage. We're obviously all very familiar with that. We have it. Most of us have it. A hot water tank on the side of our house, and that's by far the dominant form of thermal storage in the world. But it's also deployed at large scale as well, either in sort of modular systems like this example here with hot water tanks coupled to an industrial process, and sometimes in very large storage systems. For example, these pit thermal storage systems that we see across Northern Europe. We've got a lot of knowledge in the A2EP community on heat pumps, and often we see heat pump installations do include hot water storage. But of course, this type of storage is somewhat limited in the upper temperature that you can hit. So I sort of focus more on the rest of this talk on other technologies that can hit higher temperatures. The most commercially mature of those is, of course, molten salt thermal energy storage, which has been brought on by the concentrating solar thermal industry. In this type of system, basically, the salt is charged either directly, as in concentrating solar systems that are by concentrated solar energy, or it can be also charged electrically as well. Perhaps it's a very efficient kind of storage in terms of the use of the material, but perhaps a barrier is that for some industries, perhaps smaller or medium-sized industries, the complexity of managing the salt might be considered a technical risk, and to avoid things like risk of salt freezing. That said, there are some startup companies with smaller modular molten salt storage systems. So liquid storage systems like molten salt do have upper temperature limits, and that's one of the reasons that we're interested in using solids. Particle systems as a solid have this property of being very stable at very high temperatures, and particles have another interesting property that when they're fluidized by injection of air into beds of particles, they actually behave more like liquids than solids in terms of both their heat transfer and also the transport of particles. So that allows you to consider things like multiple tank systems, like shown in this example here, or single tank systems. I've got a little video which you probably hear, but I can't actually see moving on my screen, which is a system that is being developed by a company in Italy called Magaldi. So fluidized beds is certainly an interesting technology. Perhaps the most widespread in terms of at least multiple companies developing thermal energy storage systems is what I call packed bed thermal energy storage. And this is a class of storage where you have a fixed and solid bed. It could be like a sort of a system of structured packed bricks, essentially, or it could be an unstructured system like a tank or a pit full of rocks, for example. But it's a solid storage material that has some kind of fluid, often air, moving past it both to charge and to take heat out of storage. So these are some of the companies. There's a wide range of them using this type of technology. It's generally relatively simple to operate. You've got a fixed bed. Generally, it can be modularized quite easily. I guess one of the drawbacks is that sometimes these systems, particularly if you're using a fluid like air, which is not a particularly good heat transfer fluid, sometimes these systems can be difficult to effectively use all of the storage material. I mean, it comes down to sort of a costing parameter. If you can get around that by having more of the material, and if you've got cheap enough material, then that's certainly a solution. oops, just skipped over latent. So next we come to latent heat storage. Latent heat storage generally has high energy density compared to sensible storage, which is one of its key advantages. I guess some of the disadvantages is often when we're talking about a system that is changing phase from liquid to solid and back again, you're having to think about encapsulation, and also you're having to think about heat transfer and expansion and contraction and things like that. So these are some of the sort of technical challenges. But nonetheless, we've actually got a couple of very innovative Australian companies, 1414 Degrees and MGA Thermal, which have come up with really nice ways of encapsulating thermal energy storage materials into kind of brick form, as you can see here. I would say though, overall, I mean, people have been researching PCM systems for a very, very long time and a lot of pilots, and it's been a bit slower to emerge than sensible storage technologies. And then thermochemical storage, the last of these three categories, has the potential for very high energy density. And also you can see from here's just an example of a range of different reversible reactions. You can choose temperatures which are quite high, which might be corresponding to some of the processes of interest to industry. But there are a lot of challenges, and complexity and cost really have been barriers in this area. And to my knowledge, there's one company doing some current commercial development in this area, but it's again it's been very slow to emerge. I'm going to now talk just about a couple of enabling technologies. So one on the charging side, I'll just flash up this slide really. We did a deep dive looking at electrical heaters. And I guess one of the key points I wanted to make here is that some of the feedback we get from industry is that medium voltage heaters is a real enabler. The market is dominated by low voltage heaters, but when we're talking about constraints of space and also thinking about costs of transformers, for example, for many industrial sites, then there's a real advantage in having medium voltage heating, and there's a lot of emerging technologies in that space. Also, there's very interesting new technologies coming on board, things like systems where you directly pass current through storage materials, induction heating, where you're able to separate out the hot bits from the power electronics, and also turbo machinery, like in the picture here, where you can really get very high temperatures for air heating. And then, of course, coupling downstream of the test system with industrial processes is super important, and often where a lot of costs lie. The most common sort of way we think about it is through steam networks, where the coupling is actually done downstream, perhaps integrating with an existing system, maybe integrating with some conventional fossil fuel backup systems. But other processes rely on hot air. There's some processes listed here. And it's worth bearing in mind that packed bed systems where air is the heat transfer fluid actually deliver air already, and they can be used either directly or potentially in a preheat or a post-heat. So there's a lot of flexibility in how you might arrange this type of technology. Finally, just very quickly whip through the case studies that I mentioned. Probably everyone's familiar with this one. It's been on a previous A2EP seminar, the graphite energy implementation of their system at Mars, Petcare in Wodonga. This is a system providing steam into that plant. Oops, skipped on there, sorry. This is a heat pump site down in Kyneton, Victoria, where actually the storage, which is hot water storage, was really important for managing on the demand side. So abattoirs have very inconsistent demand profiles, and that was an important part of making that a viable project. This is the Sundrop Farms tomato, greenhouses here, tomato growing greenhouses. This was a system, a concentrating solar system, where the storage was done as a single tank thermocline, delivering heat into greenhouses and also into multi-effect distillation for fresh water. This is the recent installation of the MGA thermal pilot plant, and this is a system that can be, where the steam conditions can be tailored to sort of match those of many different kinds of potential customers or industries. A few international ones. This is again quite recent, multi-tank molten salt system by Kyoto. It has some really innovative features, which I haven't got time to talk about today, but it's one thing that's interesting is it was delivered under a long-term heat as a service model, and that's becoming increasingly interesting for industry, and several companies are offering that. This is another recent one by Rondo in California. Their bricks that they have, their refractory bricks, a very interesting technology. And in this case, they had their behind the meter PV plant. So they're able to use this, therefore, to sort of, buffer them essentially from some of the retail tariffs in California. That was important in that project. I mentioned here, this is a concentrating solar plant, and it's a big plant, and then they've attached to it a very small molten salt heater. I guess you can see these huge PV plants in the background, and the idea here is soaking up excess PV and putting it into the molten salt. It's a demonstration scale really here, but that's an interesting one as well. There's several companies developing electrical molten salt heating technologies at the moment. And finally, this is one I've included just because it's a fully airside one. So it recovers waste heat from a kiln. This is in France, and at about 500 degrees, and stores it in ceramic materials, and it can use that to then drive the drying of their terracotta that they have in this situation. That can be used because it's got two tanks. It can be both charging and discharging at the same time. So there's some examples. That's it for me. Hopefully that's provided a bit of an introduction to some of our other speakers. So back to you, Laura.
Excellent. Thanks so much, Joe. That was really fantastic. I think probably there'll be a few ones in there that maybe not everybody was across, and I can see we've got a few questions coming in now in the chat and Q&A boxes. So, Joe, while you're uh, moving on from your presentation, you can check out those, and we can also have a look at some at the end as well. Okay, great. Well, next we have Kris Nelson from Knode, which is a renewable heat project developer. And Kris's current focus at the moment is on the adoption of thermal energy storage solutions to decarbonize every industry and developing projects for that. So thank you, Kris. We can see your screen and you're ready to go.
Cool. Great. Thanks, Laura. Thanks, everyone, for having us. It's good to be here to chat about this. If I can just get the slide to change. Right. Cool. So, yeah, a little about us. Knode is a technology, an energy technology business with a big focus on decarbonisation in heavy industry. And we have this very strong view that thermal storage is the most viable pathway to decarbonisation. As mentioned, we work very closely with MGA Thermal, and we've done that for the last 3 years or so. Again, we're strong in our belief that MGA is the best test technology in the market at present. So we've partnered with MGA in WA, NSA, and the NT, where we're really working to drive commercialisation outcomes of the test solution. And we do this in a couple of ways. So we work supplying blocks and the test designs to customers, and we also originate test projects. Our team, we have a strong track record of commercialising technology, and a lot of our progress to date has been on the back of the innovations around how we bring that technology to market. Look, Joe did a pretty good job of covering this, but I'll just restate quickly. Industry is really heavily dependent on heat and steam for processing and manufacturing, and in doing that, it uses vast amounts of energy to achieve it. The bulk of that industrial heat comes from fossil fuels, which are also the main sources of emissions. In Australia, it's really the big heavy emitters that drive a lot of the jobs and exports. So keeping these industries operating in Australia is really crucial. And we see a genuine risk where if these industries can't decarbonise economically, then they'll either adopt a harvest strategy and operate the resource until they're no longer viable and they'll shutter them, or there's a genuine risk where they will go offshore to jurisdictions with lower carbon standards or with cheaper energy. So this is a lot of our motivation to try and solve this challenge with decarbonisation. TESS provides a viable and economic pathway to decarbonisation in that temperature range above 200 degrees and below 650 degrees where we operate. And this is something like 20% of overall heat use. And we think in this space, TESS will win. Just as a quick look across some different options, this is a collection of electric heat options that we see most often, and it's not exhaustive, but we think it's fairly representative of what's around and available in the near term. So if we go through them, hydrogen, to be blunt, has been, is, and always was a pipe dream. It's really not viable for heat. It'll always have a place in industry as a molecule, but we just don't see that happening as a heat source. E-boilers are really interesting. They're a low capex item, and they definitely have a place for intermittent heat requirements. But if your need is to produce steam around the clock and you're fully exposed to market prices, then our view is that OPEX will drive the TCO too high. Now you can offset some of those peak periods by adding a battery to the e-boiler, but as you go to scale, this is likely to blow up the capex. So we think batteries are probably an unlikely way to be an economic way to address heat. It's less efficient than directly heating as you do with a TES. And it's difficult to see the capex cost of BESS coming down to TES levels. So currently TES is about 20% of the capex cost of BESS. And these two factors sort of suggest that probably this solution of e-boiler plus BESS won't be a player at scale in industrial heat. And particularly when we're talking about heat in gigawatt hours of storage, which is where we are with heavy industry. TES capex, while it's a bit higher than e-boilers, it's relatively low, and we are fairly early in the learning curve, so you can expect those costs to drop further. TES balances capex against the ability to time shift electricity purchases. So that means you only buy energy at the cheapest parts of the day, and this significantly lowers your OPEX. So overall, your TCO is very favourable. Our MGA test also supports simultaneous charge and discharge, and that helps you in spanning that 24-hour period during the day. The other important thing about TES is we don't have some of the restrictions that BESS faces, so you can basically charge at any stage and you don't have to do it contiguously. So that means you can then have a fully opportunistic purchasing strategy. It's also worth noting there are many scenarios where the business case for adding a turbine on the back doesn't really work. So it is feasible to put a turbine behind the HRSG and generate electricity back to the market. It doesn't always work and it requires a bit of scale, but what is an alternate revenue stream is using the TES for demand response. The heaters are a very big load. They can be turned off very quickly. So there's an opportunity there to derive a secondary revenue stream from demand response. And because you have such long storage, there's enough flexibility in the system to take these payments when they're available without affecting your production. An important outcome, we finished our PFS in June last year, and what it demonstrated to us was that we can produce steam at close to parity with gas. And we're building our TES KW1 project to prove that. So, one of the big questions was how do you address the challenge of getting a TES to market, and especially a first of a kind project like this? And really that was the way we decided to break this, was to actually build a plant ourselves. It seems to be the best way to move things along. So that's what we're in the throes of doing with TES KW1. It's for a commercial customer in Kwinana. As mentioned, we completed the PFS in June last year, which showed the asset's viable. And as I say, we think it'll be at parity with gas. And the reason I say we think is in the WEM, gas prices are fairly opaque. It's quite difficult to know what an individual customer is being charged, whereas in the NEM, those gas prices are published, and we believe in that circumstance, and we are at parity or better with gas. Interesting, Joe mentioned this. So the asset will be built as a heat as a service. So it'll be an off-balance sheet asset, which provides heat to Tronox over its entire lifetime. The TES will have 12 hours of storage, and it may end up being more post the feed, and it'll charge in 6 hours, which is important because you can charge in that short window when the prices are low. And again, it can be charged and discharged simultaneously, which gives us a lot of flexibility around those charging strategies. Very importantly, for any industrial site, it has a compact footprint, and given most sites we talk to are brownfields, that's super important. We also, Joe mentioned this, which I was pleased about. So our feed design will incorporate our medium voltage heater design, and we'll talk a little bit more about that in a second. In the beginning of the presentation, I spoke about innovations required to bring the project to market. Physical technology is hard and it takes a long time. And our experience is companies won't move unless there's a significant benefit in changing technologies. So a lot of this project has been around finding ways to address these challenges and to drive that adoption. The first innovation was that heat as a service. So that was something that really changed the conversation with our customers and brought people's enthusiasm forwards. And it really was one of the accelerators for the project. And what we're finding is as we talk to more customers, this has increasingly been a discussion point. So it really does show there are a lot of capital constraints in heavy industry. The project, the PFS was actually funded originally by a consortium, which allowed us to de-risk the project for all the parties concerned. And it has allowed that rapid progress. The consortium model is one we'll use going forwards, and we have subscriber seats available in our feed. So if you're considering TES as a solution, this is a cheap way to get a deep understanding of the techno-economics and to participate in a forum with a group of non-competitive industry peers. So our belief is that MGA thermal has a technology edge in the market. MGA blocks store energy in the phase change, as Joe mentioned, and we see latent heat storage has some advantages over sensible heat as a storage medium, particularly around the very high energy density, which is 2 to 3 times that of a sensible heat product, and in the very even discharge profile. That discharge profile is crucial because MGA blocks discharge at an even temperature over the whole duration of the storage. They can easily stay above the outlet temperature. And what this means is you don't need to heat to very high temperatures in order to stay above that outlet. And so the temperatures we operate at are well below 900 degrees. Because of this, you can use the medium voltage heaters, which have some significant CapEx and OpEx advantages, particularly around less transformers, a smaller transformer yard. You require less heaters, less wires, so less copper, less instrumentation. And then on the OpEx side, you have lower losses, so that's savings as well. So overall, this means it's an easier solution to implement, and the design primarily uses off-the-shelf components, which de-risk the commercialization, but it also provides operational certainty. And importantly, you don't end up with this sort of funky high-temperature engineering, which can cause you problems. So TES really is getting ready for prime time for heat requirements for 200 degrees and above on sites of all sizes. Our feed study for TES KW1 will kick off at the end of next month. It'll be a 9 to 10 month study. So we're expecting to be completed by early February next year, and we'll hopefully move to construction not too long after that. We are very excited about the project. You can see that this will prove TES commercially, and not just for MGA. We think it's good for a range of technologies, which importantly, it also provides a demonstrated pathway to decarbonised heat, which will play an important role in keeping industry and jobs in Australia. We are, as mentioned, still looking for consortium participants, and there are a couple of subscription options for that. So we're always happy to chat about that or talk about TES in industrial settings. So please get in touch if you'd like to have a chat.
Excellent.
Thanks, Laura.
Excellent. Thanks, Kris. And now our next presentation, we have Lawry from Deta sharing the slides. Thank you very much. Now, this is a joint presentation about a thermal storage feasibility study, which Deta completed for Lenin Services Australia. This study was funded through the Australian Industry Renewable Heat Accelerator. So there was a grant for that one to fund the feasibility study, and that's what we're going to be hearing about today. So Lawry, I'll start with, is a senior engineer at Deta Consulting. He specialises in industrial decarbonisation and electrification. He has extensive expertise in designing and implementing electrical thermal energy storage solutions to help industrial facilities. Now, along with Kris, we will have Mark Rogerson and Lenin VD from Lenin Services Australia. Mark, interestingly, is a qualified chef with 3 decades of experience working in food manufacturing, but most recently he has 7 years of executive leadership in the linen industry. So he has a wide perspective on heat use from that. And then Lenin is the maintenance manager for Lenin Services Australia. He has more than 30 years experience in engineering and manufacturing environments, including automation, fast-moving consumer goods and linen services as well. So I will hand over now to Kris if you would like to come off mute. There we go. Thank you, Kris.
Thanks very much, Laura. And I think Mark's going to give a little bit of an intro around
Okay.
Linen Services Australia Dandenong facility. Mark.
Yeah, thank you, Kris. Thanks, Laura. And thank you, everybody, for the invitation to be today. Very excited to be a part of this process. I'm the General Manager of Linen Services Australia in Dandenong. We are a facility that runs 5.5 days per week. We have approximately 240 staff employed on site and off site. We wash approximately 500 tonnes of soil linen every week. Our customers range from large public hospitals, private hospitals, other healthcare facilities, aged care facilities, medical centres, and we've also started moving into the hotel and accommodation sector. We do have ISO 9001 accreditation, which means that we do have very high, safe, hygienic standards that have to be employed across all facets of our business, both the washing and the selling of clean linen or rental linen to our customers. By doing that, the Dandenong facility has 4 continuous batch washers. They are basically massive corkscrew washing machines. We have industrial dryers, and we also have automated conveyor systems and high capacity, high speed ironing and folding machines. The healthcare sector requires strict linen hygiene practices. So we do have controlled washing temperatures for thermal disinfection. We have chemical dosing for the chemical disinfection. We also have Class A water treatment and quality monitoring processes that look at our linen and how it comes out after it's been washed to ensure that our customers are receiving a hygienically clean product. The energy and sustainability for us is very important. We are owned by Macquarie Asset Management Group, and one of their key targets is to reduce energy and increase sustainability across all of their businesses. So we are happy to be a part of the energy efficiency studies, optimising steam and heat usage, evaluating new technologies such as electric boilers as a way of reducing the energy consumption and improving our sustainability. Linen Services Australia continues to focus on safe and hygienic linen processes, operational efficiency, energy optimisation and sustainable solutions for the future. Thank you, Laura. Thanks, Kris.
Thanks very much, Mark. And thank you everyone else for being here today. So yes, so we were engaged by Linen Services Australia to complete a feasibility study on thermal energy storage. And that was funded through, as Laura mentioned, the Industry Renewable Heat Accelerator, which has funded a number of studies across industrial, decarbonising industrial heat. And so, yeah, very happy to, very thankful for the accelerator for providing us with this funding. I guess one of the key things that maybe we should talk about just quickly is why are we doing this? The key reason that Linen Services Australia is interested in this from one perspective is de-risking their industrial heat or the cost of their industrial heat. As we're all aware, I think we're all aware, price of natural gas has been increasing over time. And, we experienced a large price shock during the Ukraine war, and we may be looking at another price shock coming with the current conflict in Iran. And there is a lot of talk in the media around the price of electricity increasing, but the rate at which the price of electricity is increasing is nowhere near the same as natural gas. And the key thing to point out that we've seen is that the midday price of electricity has been continuing to fall. So that is what's driving this. So what can we do to help industrial heat users like Linen Services Australia to access that low-cost midday electricity? In addition to the price of electricity, the spot market for electricity decreasing in the middle of the day, network companies are also identifying that they need to try and motivate customers to move to midday electricity consumption away from peak electricity. Linen Services Australia is located in Dandenong, just south of Melbourne, in the United Energy Network. And the United Energy Network is now offering a published tariff, which is really, really supportive of these types of projects. So going from their standard tariff, which is around 7 cents per kilowatt hour, to a new tariff, which is where the cost of electricity or the network charges are around 0.7 to 0.9 of a cent per kilowatt hour, as long as you avoid that peak electricity, peak demand time of 4 to 9 p.m. at night. So again, all of the things are starting to align that if we can use electricity during the middle of the day, this can offer significant cost benefits and also provide additional stability to the grid in the middle of the day, where we start seeing grids start experiencing things such like minimum system load. So the first thing that we did with this project was we wanted to map out what all the energy use is on site. So we completed an end-use breakdown of the natural gas on site, both in terms of the amount of energy used by each of the different processes and also when it's used on site. So the key thing to note here is that Linen Services Australia Dandenong facility significantly uses a significant amount of natural gas directly in their dryers. And then steam is predominantly, natural gas is also used in boilers to produce steam, but that's predominantly only used in the washing processes. And that is a limiting factor for this because it means that we can't electrify a lot of those dryers before they are converted to steam dryers. So there are direct natural gas dryers, there are direct steam dryers, or there are steam dryers. Both have very similar efficiencies. So for the Dandenong site, there's definitely a drawback not using steam dryers on site. But other facilities definitely do use steam dryers. The other thing to point out is that the facility predominantly operates during the daytime. So it operates from 6 a.m. in the morning through to 10 p.m. at night is the bulk of their energy consumption. And that is 6 days or 5 days a week plus a half day on a Saturday. And in terms of electrical capacity, the site was found to have significant available electrical capacity. So it's got 3 MVA of electrical connection, and they're only using around 1 MVA, and that's only generally used during that 6 a.m. to 10 p.m. period. And that'll be of interest when I talk about electric boilers near the end as well. So the first thing was we looked at electric thermal energy storage, or eTES. And we looked at a range of different technologies, but we looked at the 3 main Australian manufacturers, so Graphite Energy, 1414, and MGA Thermal. They're all based on very similar technology where we're heating a solid medium up with electricity at low voltage, so 415 volts was all of the designs that we looked at, and producing steam for the site at 12 bar. So very much within the temperature range of these units. And the plan is to keep the existing natural gas boilers running in parallel. In terms of footprint for the site, the eTES units do take up a significant amount of footprint compared to a standard natural gas boiler. So if you look on the diagram here, the traditional boiler house is located down here, and that has 2 natural gas boilers located inside of it. If we're going to install an eTES unit, it would need to be installed either out here in this footprint of 11 by 20 meters, or even over the back here in the 17 by 32 meter slot. As you can see, they are a fairly significant unit. So this is an example of a Rondo unit that was installed in Thailand, and that is a 20-foot shipping container at the end of the unit. So yeah, it is a significant footprint, and so having space on site is important. It is probably worth noting that these Rondo units can go vertically a lot higher, so you may not require much more footprint than this to do 100 megawatt storage, or maybe even 150 megawatt storage, but it is a lot larger than what we're normally used to in terms of steam boilers or natural gas steam boilers. So we completed some very detailed analysis of the AEMO spot rate, the environmental charges and the regulator charges. And what we found is that the average electricity price came out to around 1 cent per kilowatt hour, which is really competitive. And the key thing to note here is that most of that actually comes from environmental charges and largely from beaks. So when you actually if you're in states that don't have those type of state certificates, then this number may be lower. But the key thing is that Victoria does have a very low spot rate, so it does tend to balance out. And when you compare that to the spot or to the price of natural gas, which we found to range between 5 and 15 cents per kilowatt hour, you can see that we can be well below the price of, the combined price of electricity can be well below the price of natural gas. And if we saw that natural gas price increase, we could be potentially below the natural gas price 50% of every day, or 50% of days, hours throughout the year. And then that spot price on a half-hourly basis then followed through to us modelling out when the eTES unit would be operating, times of the day. And so what we can see here is in the green, we're modelling out the steam demand and whether it's coming from the thermal energy storage or whether it's coming from the natural gas boiler. Now, what I would say is that for most of the year, this graph is all green. So for January, February, March, especially all green because there's lots of excess solar. But when you look at July, August, you see that most of this graph would actually be purple on previous data. I've just picked 1 month that shows both, 1 week that shows both of those units operating. So what we found was the energy saving for the steam boilers was 76%, but that only offset 31% of the site's natural gas because a lot of natural gas is going directly to those steam boilers. And then on the right, we've also got the charge within the TES unit throughout a weekly profile, where we're doing a bulk of that charging over the weekend. The last thing on the thermal energy storage to talk about is the payback period. So where the rubber meets the road, where everyone's really interested, is how much does it cost and what's the payback? So if we are looking at for the unit for the site, we roughly estimated around $12 million all in, everything installed on the current market price, including electrical upgrades, everything like that. And that results in a payback period a lot longer than most companies are willing to accept. 18 to 20 years is kind of where we are without any government funding. If you looked at the perspective where you say, for example, we got 50% co-funding from ARENA, you're down closer to that 10-year mark. And then if we are able to get efficiencies of scale, or the price of natural gas increases, then all of a sudden we're getting closer to that 5-year period, 5 to 7 year period. So it just really depends on what your outlook for the market is. These economics significantly change if you're also on LPG as well, where the price of LPG is much higher. So overall, based on looking at this, we found there's a number of different factors that contribute to whether eTES is suitable for different sites. So this is a little bit of a cheat sheet for people to quickly run through to understand whether they think it's suitable for their sites. So how much steam are you using? How consistent is it? It's not well suited to the industries where you're only operating, say, for example, a milk processing facility where you're only operating 8 months of the year or 6 months of the year. You really want the plant to be running very consistent. High price of natural gas always helps. Low price of electricity, favorable network tariffs, and then that's obviously weighed up against environmental charges depending on what state you're in. And then, the site fit. So have you got the space to actually take the eTES unit, and have you got the availability to take the for the electrical capacity? And then last of all is ARENA funding, or state funding, even in New South Wales now. My last slide is just talking about one other option that we looked at for the site. So we also looked at an e-boiler. And the reason we looked at an electric boiler for this site is because the site's predominantly operating during the day. So we thought, as Kris Nelson mentioned in his original slide, electric boilers do come with a much lower capex cost. So can we offset a large amount of the natural gas at a fraction of the capital? And the answer is yes, because they're operating predominantly during the day. And so what we found is that by installing an e-boiler, we could offset 45% of the natural gas, 16% of the total sites, 16% of the site's total natural gas, and we can do that for a fraction of the cost. And so I'll show you and that's what it would look like in terms of that operating profile as well, and when it's operating during the week. And the key thing here is that the actual estimated cost of the electric boiler installed was somewhere around this $1 million mark, because the site already has sufficient electrical capacity to take the e-boiler. They've already got the footprint inside the boiler room for taking it, very close to the steam manifold. So the cost of install becomes quite low. And so, the payback can be somewhere around this 2.5 through to 4 year period, which is well within most companies' expected payback period. And if we can even drive that down even further to $750,000 for the installation, we can get under 2 years. So that may be an option if we're not looking for complete decarbonisation. This may be an option to get them started on this journey while they go through the process of replacing dryers with steam dryers over time, and it might be a good interim step. And I think that's all that I've got today.
That was fantastic. Thank you, Kris, and thank you also, Mark, for introducing your operations and the challenge that you had there. I think that's a really good point there at the end, Kris, is that people often think, gee, we have to do everything right now all at once, whereas no, this can be a transition. You can do a part solution to get you on your way while you work out maybe some of the trickier challenges along the road. So it's great to show that there. Thank you very much. And now I'm going to hand over to Jared Leake, CEO of A2EP, to take us through some of the questions that have come through the Q&A box. If you'd like to add any more questions, please do so. We're happy to get to those. I think we've got a bit of time. Jared, over to you.
Thank you so much, Laura. Gee, there were some good presentations there, dropping gold there from each speaker. So thank you so much there. And we'll get into maybe a recap a bit at the end here. But let's jump into some questions that we've got coming through. Joe, you've already answered one of those. Type that in. There was a commentary there on some other eTES type solutions that both you and I have not heard of. Rift or something in there?
I mean, there was just Altero and Rift.
Yes.
Yeah, I mean, the question was, are these thermal storage? I mean, I would just anything that they sound like thermochemical storage systems, which I mentioned in my talk. Things where, like iron oxide, for example, can be regenerated, redox sort of process. So I'd have to look into it a bit more. I've classified thermochemical as thermal energy storage in the very, very broadest sense. But yeah, it's good to hear that there's some other developers working in this space. It's been a very tough one, as I mentioned in my talk. So
yeah, and the other one that I put in the chat there was Cache Energy, which I've only just become aware of in the last month or two, which looks promising, but feels a bit more risk involved with the longevity of how that performs over time versus these more simpler methods of latent and sensible heat. So interesting. But thanks, Joe. Look, we've both got some homework there, which is good. Further questions there. Rick Waters, thanks, sending a few through, keeping us busy there. One came through to Chris Nelson. Some questions on timing and what have you for the MGA Thermal and Tronics project. Maybe you'd like to share a bit more on that one, Kris.
Yeah, sure. No worries. Thanks, Rick. So as I mentioned, FEED is scheduled to start end of next month. And there'll be some announcements about that. We're just not in a position to talk too much yet about what's going on, but that's all about to become public. So that should go to kind of end of Jan, early Feb next year is what we'd expect. We're hoping to start construction not long after that. It's obviously pending some further discussions around funding. So that happens during the course of the feed. That being the case, we'd be operational in 2028. So I couldn't give you a date yet on that, but that's the target.
So 2028, 6 months or so, I guess, before you really start seeing some good data coming out of that, I guess.
Yeah, so that was, so we'll obviously, again, I can't share what's going on there. There will be data available publicly. We have a data sharing obligation. And then obviously, partners in our consortium, if you're looking for detailed data, that's where that's available as well. So
great. And I'll put in my calendar for a site tour come 2028 as well there, Kris. We'll see if we can get over.
I'd love to show you around.
Yeah, fabulous. Good on you. Let's have a look at a few more questions come through there. Let's go to the one from Ken. This is for Mark and Kris Lawry. Talking about AI data centers and their energy and water hungry. Generally, is that a concern for energy and the AI? And then more specifically, what about the what's being done on site to reduce water consumption along with electricity there?
Yes, so I can take this one on. So I've spent a fair amount of time on the Dandenong LSA Dandenong site, and they have a number of water saving equipment in place. So they do a fantastic job of recycling huge amounts of the water on site, treating it, cleaning out to really minimize the amount of water that's used. Those continuous batch washers that Mark spoke about are extremely water efficient. The other work that we've done through previous projects at the LSA Dandenong site are focused on using things like heat pumps to recover heat from their waste stream as it leaves the site, which means that we're decreasing the amount of water we're sending through cooling towers. So that again reduces the amount of energy. And I think in terms of the AI data centers, the key thing to understand with AI data centers is that their energy consumption profile is very flat. And so the key thing here with these type of thermal energy storage systems is we are trying to make sure that in the middle of the day, when there is very low energy consumption from the grid, that we're trying to suck up that low cost, potentially curtailed renewable energy in the middle of the day and not add to that peak during the nighttime evening point. That's really the critical part of this compared to a data center, which just is almost a square curve, 24 hours a day, 365 days a year.
Gotcha. Thank you so much, Kris. And on that, just while we got you there, pretty exciting tariff you've got there from United Energy. Coming through at almost zero energy costs there. That's fabulous.
Well, it's actually 0 cents per kilowatt hour is the tariff for all United Energy, Power Core, and City Power. All of those fall under the same group. And then the only cost that comes in is a fixed demand charge. So the fixed demand charge is $1,500 per megawatt per month, if I remember off the top of my head. And that's where that rough 0.75 cents per kilowatt hour comes from. But it's actually just a fixed demand charge at 0 cents per kilowatt hour.
Yeah, well, it just really helps that eTES a lot. So I know United does that. Then that means also then Power Core, because they work together, have something similar.
Correct.
And I know Essential Energy does something as well. But we've got a fair few distributors yet to get on board with these sorts of offerings. Yeah.
Yeah, and we're working on it. We're working with distributors across all states to try and promote these types of tariffs and the benefits they offer with things like minimum system load.
Yeah, gotcha. A question here from Paul Gorick, and I think this one will be to both Kris's. Whilst there's not a lot of eTES out there operating and working in conjunction with existing boilers, any thoughts? Is there any early thoughts on how that you can integrate with existing boilers and what's going to be required there?
I'll have a go if you like, Kris. Yeah, look, from our perspective, e-boilers definitely have a place, and we will look at an option which includes an e-boiler in our design, and that's partly for just to get volume through during those cheap parts of the day, and arguably for redundancy. But my suspicion is we probably in this first instance won't end up with that, but that's to be decided. But it's definitely in consideration. So, and I think too, this highlights nicely the difference between 24-hour operation and intermittent operation, where we're generally dealing with people looking for round-the-clock heat and steam. So, we scale for that and design for that, and probably for that reason we won't need an e-boiler. But interesting on the tariffs too to that point.
Yeah, and in terms of, from our perspective, the integration of thermal storage with an existing natural gas boiler is a fairly easy integration to do because you have quite a long lead in before you get to a percentage charge. So, say below 10% charge, you will start spinning up the natural gas boiler, and that's quite a long lead in. It's a far harder thing to integrate an electric boiler with a natural gas boiler because the timeline between when they start and stop is a lot shorter. And so you may need to do some modeling and put in things like steam accumulators to manage those surges between, or the switcher between the two.
Thanks. And Kris, while I've got you there, question about the dryers there. Did you look at changing them from steam to hot air, or maybe that might be one for more for Mark and Lennon? More thoughts on that?
We have looked at like there are commercially available steam dryers on the market. It is considered kind of an older technology, but they do have a lot of benefits because you don't have any risks of fire. You tend to get a better product out the end of the dryers in terms of the heating profile. So there are a lot of operational benefits. It's just a case of that they were moved away from for an efficiency point of view. But if you went around the industrial laundries in Australia, you'd probably find a 60-40 split of steam dryers to natural gas dryers. So there's more natural gas dryers than there are steam dryers, but there's pros and cons both ways.
Good, thanks, Kris. And you got a big nod from Mark there, talking about the quality of the dryer and things like that. Nailed it, mate. Thank you. Final question, and mate, I'm not sure Joe's done much work on policy, but I'll have a crack at this as well as key government policy initiatives to increase the uptake of these technologies. Joe, I'll kick off with my favourite two at the moment, and we're waiting for AEMC to come out with a consultation paper to submit this to them. Number one, incentivizing distributors for grid utilization rather than just on their RAB. So let's get them focused on that. Number two, forcing them to have flexible demand tariffs, like United, Powercore, and Essential does. They all 13 or so need to do it. Joe, any thoughts from you?
Oh, no, I was actually going to pick up on that first one you made, which is, I mean, thermal energy storage is excellent for grid utilization, for generally increasing, using what we have in the existing electricity network. Whereas, electric boilers, while there's, at the site, it might be quite cost effective. And, often though, you're going to have to actually upgrade for those peak periods. So I think really sharing benefit, I guess, is the thing. The site is installing the test system, doesn't always see the benefits that are happening elsewhere across the electricity network. So policies that address that imbalance, I think, would be good.
Awesome. Thanks, Joe. Laura, back to you. Great
Yep.
content today. Love the cheat sheet from Deta. Love hearing about 500 tons a week of linen going through and some insights on this contiguous charging from BESS versus TESS. So that was great. But back to you now.
Excellent. Thank you, Jared. And whoops, going too far back. Okay, I just wanted to quickly let you know about some upcoming events that we have from A to EP. Tomorrow night we are having our member update meeting in Sydney, followed by networking drinks, and we're going to have some brief presentations from New South Wales DQ, RSM Australia, Borg, AGL, Design Better, MGA Thermal, and Inner West Council. So if you're a member, please do register for that. You can find it on our website. And then we've also got a Brisbane member update coming, and we've got some workshops on lowering heating hot water, which is really a game changer for the electrification of commercial buildings. It can really bring down that upfront capex for the heat pumps to replace gas boilers. So we have workshops coming up in Sydney and in Melbourne. So again, we will send links to that in the email to follow up this webinar. And if you're interested in today's topic, you will love our Australasian Renewable Heat Conference coming up in September. We've already had a lot of interest in this event. We've got Victorian Government as our diamond sponsor. Thank you very much to them, but also Origin Energy as a platinum sponsor, Becca and Essential Energy coming on as gold sponsors, and many others. We still have a couple of sponsorship packages and some places in the exhibitor area. So please visit the website there. You've got the link there. And if you give me 20 minutes after this webinar, I will press go on the registrations and you can lock that in for September 2nd and 3rd in Melbourne, our third year of this conference. It's really focused on action and accelerating the decarbonisation of industrial heat that we've been talking about today. And then just finally, just to keep up with A2EP, please follow us on LinkedIn. We try to do posts on a range of topics that will be interested to anyone that has come along to the webinar today. So you can just search for A2EP on LinkedIn and you will find us. Apart from that, I would like to say thank you very much to our presenters for their excellent summaries and briefings today. It was really fantastic to get that whole overview of the technologies and what's the potential for the market in Australia, and then to come to the end user perspective as well, and then the project developer's perspective from Kris from Knode. So thank you all very much for your time. Slides and recording coming next week. Thank you, everybody.